This lecture is a little long. I'm going to apologize. It's probably too many slides. The first half of it we're going to go through quickly. Now, hopefully you had some time to look at this document. This is a document that I wrote most of it, but also had some help from Gaurav Savanaverdick and Ronnie Heath. Okay, and you can get it online here. You just go to the RAS page and find it. It's there. But you had a reading assignment, and specifically Chapter 6 last night, which this lecture is based on. So what we're going to cover is we're going to talk about some definitions of 1D versus 2D equations. And we're also going to talk about knowledge of the river system and purpose of the hydraulic model, data requirements for 1D and 2D models, and output results. And then we're going to get into the 1D versus 2D modeling differences. So the first four topics we're going to go through really quickly. It's about half the slides because it's just general information. It's stuff you can read and understand very easily if you haven't already read it last night. Okay, so we're going to go through these first half of the slides quick, but then we'll spend more time on the second half. Okay, so definition. So in general, all fluid is really three-dimensional, okay, for the most part. Even in a canal, there's velocity accelerations up and down and left and right, even though the predominant velocities are down the canal. But very often for certain types of problems, we can dial back the three-dimensional equations to either a two-dimensional form or a one-dimensional form because the predominant forces are either in one or two directions. So a definition for 1D modeling is the equations are derived under the assumption that the predominant forces that are acting on the body of water are in the x direction along the river, up and down the river. And if those are the dominant forces, ignoring the lateral forces and the forces going up and down in the water column might not be so bad. And so then using a 1D equation set can still give very good answers. 2D modeling, the equations are derived under the assumption that the forces that are acting on a body of water are predominantly in the x direction, up and down the stream, but also laterally left and right. And then the vertical accelerations of the water column are considered to be negligible. And if that's the case, then 2D equations can do a great job. Okay, so that's the basic definitions of what we're doing with the equations. Now, there's a lot of things you need to understand before deciding, am I going to use a 1D set of equations or 2D? And that's what we're going to talk about at first. Okay, so right off the bat, well, how big is the system that I'm going to model? Is it less than a mile? Is it 10 miles, 50, 100, 500, 1,000? What is it? If I have a system like on the right, this Allegheny River system, this system has thousands of miles of river system. There's no way I'm going to be able to develop a detailed 2D model of that entire system and run it in any reasonable amount of time. It just isn't going to work. So that kind of system really needs to be 1D or predominantly 1D with maybe some small 2D areas, okay? But if I have much smaller problems, like maybe I'm only just studying a bridge, well, that is easily something I can do completely in 2D because it's very small. The next question you need to ask yourself, well, what's the complexity of the system you modeled? One really important question, is it hydraulically steep? Does it have steep areas in parts of it? And the reason for understanding that is steep systems are much more difficult to model than flat systems because in steep systems, we have higher velocities, we have more rapid changes in water surface and depth, area, and velocity, which means we're going to need smaller cells or tighter cross-section spacing, smaller time steps, et cetera, et cetera. But the other part of this is what hydraulic structures do we have out there? Are there lots of bridges and culverts? Are there dams, weirs, gated structures, levees? How many structures and types of structures do I need to model? And are there any special operating rules for those structures? And another thing to know up front is the flow path of the water generally known for the full range of events? In other words, do you know where the water's going to go for the full range of events? If you don't, there's no way you can lay out a 1D model a priori, because to lay out a 1D model cross sections, you have to lay out the cross sections perpendicular to the flow, which means you know and understand where the flow is going to go. Okay, so if you don't know the flow path of the water, especially out in the overbank area, then a 2D model is going to be easier to do because you don't have to know the flow path. It'll compute that for you. Okay. And the other problem is, what if the flow path can change during the event? Well, 1D model can't handle that. And if you were doing 1D modeling, you might have to create two separate geometries for the different events, one for low flow events and one for high flow events to capture the fact that the water's changing direction and going in a different direction for that higher flow versus low flow, where a 2D model can handle that straight out of the box. Are there any unique aspects of the system that will significantly affect the computed results, such as it tidally influenced? Now 1D and 2D can handle tides, but it depends on what you want to get out of that tidal area, okay? Does wind speed affect the water surface? If you have wind that dramatically affects water surfaces, generally those water surfaces are going to be affected in multiple dimensions horizontally because the wind doesn't stay in one direction, just up and down the river. It's coming across and laterally, so that's where a 2D model is going to do a better job. Floating ice and ice jams, do you have that? Is there debris? And does there debris hang up on the structures? Do you have levees that are going to be overtopped and breach? And again, are there any unique hydraulic structures that require specialized modeling or gate operations? Those are the things you need to know up front. And then of course, what's the purpose of the model? There's lots of different models for different purposes. And so these are just some of the things you might be asked to do as an engineer. So the first one is, what if you're asked to develop a really quick model? You know, it's just going to be rough. I need answers quickly, okay? Well, you're generally going to use 1D or 2D models but they're not going to be very detailed. And the reality of it is, with the tools we have in RAS, it's actually faster to generate a rough 2D model than it is a rough 1D model, because it's very easy to generate a polygon, put in a grid size, make some base n values, attach boundary conditions, and run it and get maps, okay? That you can do that a lot faster than laying out a 1D model, but it's still a very rough model. Now, what if you're doing a detailed planning study? Again, it could be 1D model, 2D, or combined 1D and 2D for planning studies. It depends on the situation of the river system and the hydraulics of the river system. Design study. If you're doing design of structures like gates or weirs or overflow spillways, you can use 1D and 2D models kind of like preliminary screening tools, but that really final design should be 3D, okay, or physical models or both. Now, if you're just doing the design of a levee height and the river is predominantly one-dimensional flow, you can still do that with a 1D model, because the 1D model is going to capture the water surface accurately. And when you're designing a levee height, you're really just looking at, well, how high do I need to make the levee? So that could still be done with 1D. And then as far as developing models for real-time modeling and mapping, it gets into runtimes. Maybe you want to use 2D modeling for everything, but it's just too slow. So you might have to back off and do some combined 1D and 2D modeling, or if the system's really big, you might have to do 1D only. Sources and accuracy of data, okay? You got to know the level of detail of actually your train data, if you had any surveyed cross sections, living information, hydraulic structures. You also need to know what's your data for your hydrology and boundary conditions. Do you have peak flows only, full hydrographs at gauges, or do you have a hydrologic model you can generate flow hydrographs anywhere? And then duration of events to be modeled. This is going to depend a little bit on the size of the watershed and study purpose, but you might be looking anywhere from steady flow, or in other words, just peak flows, a snapshot in time. That's 1D, 2D, or even 3D. Single events, you know, less than a day to months, that could be 1D or 2D. But once you start getting into period of record analysis, like you want to do 100 years of record, you might not be able to do a complete 2D detailed model unless that area is very small. It just might take too long to run. And so that's where you might have to do 1D or combined 1D and 2D if you're going to do period of record analysis. So data requirements can be significantly different for 1D and 2D modeling approaches, you know, depending upon the problem. So the amount and quality of available data, you know, can vary. And the main things that we're going to look at for that are terrain, roughness, structures, and calibration data. So terrain data, you know, we can drive and have been driving 1D models for 60, 70 years with just surveyed cross sections. We don't even need a terrain model, okay? But as soon as we go to do 2D modeling, we have to have a terrain model, okay? And in fact, the quality of that terrain model is going to affect the choice, because if we have no underwater channel data, then it's a lot easier to add in the channel into 1D cross sections than it is to create a detailed underwater channel for the entire terrain model, which may not be possible, okay, depending upon what kind of data you have. Here's just some examples. So on the left is a terrain model where there was no underwater channel data and the bridges were still blocking. This is really not even usable for a 2D model, because we can't push water through the bridges if they're blocking the channel. And plus the channel just doesn't reflect the underwater. So we made a cross section. We took cross sections and made a terrain model of the cross section like you did in your workshop, and then merged that in. So now on the right, we have a model that we could use for 2D modeling, a terrain model. Here's just on the left, I've got detailed LiDAR. On the right, I just have a USGS 10-meter DM. You can see that, you know, the levee is way more accurately represented with the LiDAR data, whereas with the 10-meter DM, it's just, hardly there. It's just in bits and pieces. I also don't have any water channel data underneath the water surface in the 10-meter DM. There's just no channel data underneath the water surface. Over here, that could have been supplemented and made together. So if you're going to use 10-meter DEMs, you're really missing a lot. First of all, you don't have any data in the channel underneath the water surface, period. It's just not there. And you're not going to pick up things like levees accurately or buildings or anything. Okay, channel and floodplain roughness. In 1D modeling, we can just change the N values right in the cross-section editor. We don't have to have spatially varied land use, but you can. So now, especially in RAS 6.0, we can cut N values from our land cover data sets, which we didn't have before. But in 2D modeling, that's the only approach. You have to have spatially varied land use information and layout N values in order to get an N value at every face. There's no way to do that by hand. It wouldn't make any sense. And here's just an example of a land coverage like you created. And here for the channel, I have a separate classification for the channel. Okay, and so I can show that I can get different channel values versus overbank, and I can also do calibration regions and override that, which is a necessity for 2D modeling, where we don't really need to do that for 1D modeling at all, to be honest. Hydraulic structures. For 1D models, we generally use physics-based equations like energy and momentum and cross-sections and roughness values, but there's also empirical equations that we can use for things like pressure flow and weir flow and gate flow, etc. And we also might have rating curves that we can put in. In 2D modeling, we have all those same approaches because we can add in what I would call 1D hydraulic structures inside of a 2D model using the same exact approaches as we did in 1D. But we also have the option of saying, well, let's forget the empirical equations and let's just model the flow through the structure, maybe like a bridge or a gate that's completely open as two-dimensional flow with really small cells, okay? But that's going to require a much more detailed terrain model to accurately describe those structures and in the inside of the structure, as well as possibly turning on eddy viscosity coefficients and calibrating those. Here's an example of a really detailed model of 17th Street Canal and modeling the gate openings. Again, these gates are completely out of the water, so it's just flow going through the gate openings, which we can do in great detail with a 2D model. Okay. Calibration and verification data, okay. For 1D modeling, we need observed flow and stage hydrographs and gauges, as well as high water marks where we can get them, and possibly any historical inundation maps if those exist. In 2D modeling, we need the same exact things, but we might also want to get observed velocities, because if our 2D model, if understanding the velocity in the channel is really important to the study, we might want to see, well, how well does it actually do against observed data? Or am I just going in blind assuming the velocities are good? Okay. And then model outputs. One of the things you need to ask yourself up front are, and ask the planners and people in charge of the study, okay, what are the required hydraulic results needed for the study? What level of detail is needed for the study? What level of accuracy is expected or desired for this study? So you need to ask those questions up front so you know what you're being asked to do. And then that might lead you into one modeling choice over another. Now in the document, I have this table. I'm not going to go through it, but what I tried to do here is lay out different types of hydraulic outputs and what you actually get from a 1D model versus a 2D model and a 3D model. And I'm going to let you read that on your own, but it'll let you know in what you can get out of these different modeling approaches for these kinds of variables, okay? Now, of course, if we're looking at output and we're looking at water surface, for a 1D model, we can only get at every cross-section one water surface at any instant in time. And obviously for a 2D model, the water surface can vary depending upon what's happening and how many cells we have across that channel or floodplain. For velocities, in a 1D model, it really only computes an average velocity in the left overbank, an average velocity for the channel, and an average velocity for the right overbank. Now you can request to have that slice that up and give you more variable water surfaces, but those water surfaces weren't computed with the hydraulics equations. They're just being computed assuming that for this one cross section, we can look at the conveyance and the slices and distribute the flow and then distribute the velocity without any knowledge of what's happening upstream or downstream of this cross section. Whereas with the 2D model, we're going to get varying velocities actually computed based on the number of cells we have across the channel in the floodplain, And those velocities really are computed with a two-dimensional momentum equation. So it's more detailed. And the effects of what's happening upstream and downstream of this will have an impact on those velocities that are computed. Inundation mapping, if I did this upper map with 1D cross sections and storage areas and overbank, I might get a map that looks very disconnected because if there's a large elevation change, I'm going from one storage area to another, and in a storage area, I can only have a single water surface at one time, so the map's kind of disconnected. Whereas if I model that with a 2D flow area, I can track where the water's going and all the flow paths accurately, both spatially and in time. Okay, let's get into the second part of this now, where we're really getting into the 1D versus 2D stuff. And we're going to start out with, okay, water surfaces. We already saw this plot, and we already discussed that. So again, in 2D, we're going to get variable water surfaces spatially, not just in the channel, but throughout the model. But in 1D, we get one water surface per cross-section and one water surface per storage area at any instant in time. Now, velocities, this is kind of a cool plot, and I'm going to go ahead and animate these two things. And so on the left, I have the exact same reach of river and same flow rate modeled completely with 1D cross sections. On the right, I have the exact same reach of river modeled with the same flow rate in 2D. And so what I want to point out here is some obvious differences. So through this bridge up here, the 1D is not showing much velocity, showing a high velocity upstream. But notice in the 2D, the lower velocity is upstream and it gets to a higher velocity in the structure because it's contracted more. Well, that's obviously more accurate because this bridge abutment is impinging this flow and causing it to contract and causing an acceleration right in this zone, which makes physical sense. Notice also when the water comes out of this bridge, there's a recirculation zone. I can't get anything like that in 1D. In fact, it shows the water all going straight, like it's going right through the embankment, even though it's not, okay? Because it's only plotting velocities based on cross sections outside and then the ones inside the structure. And then here, the water expands back out, and then it has to contract sharply to get through the bridge opening. Here it expands out, but it's not contracting sharply as far as, because the velocity is just based on the 1D cross section upstream of this. And it has no knowledge at this point, the cross section here has no knowledge of this embankment causing the water to actually contract really sharply, unless I put some ineffective flow areas in there, which I can do, okay? And then down here, we've got another recirculation zone. 1D can't predict that, etc. So I get very different velocities from the standpoint of maximums at different locations, as well as how the water's moving, contraction, expansion of the flow, eddy zones that I can see in much greater detail with 2D over 1D. Okay, computational spacing. So 1D cross-section spacing and 2D cell size are very similar as far as the requirements for the size of the cells versus how far apart I space the cross-sections. So in general, I need to place cross-sections or create cell sizes that capture and describe the changes in the geometry, okay? So if the geometry is changing rapidly, I need smaller cell sizes to capture that or tighter cross-section spacing. Additionally, I need more cross-sections and cells are needed if I have significant changes in water surface, ground slope, velocity, and roughness in order to pick those things up. I also need to add cells around levees, bridges, culverts, and structures, as well as cross-section to pick those things up more accurately. And then you need to think about bed slopes. Steeper slopes require smaller cells or tighter cross-section spacing because the water surface is changing more rapidly, the depth and velocity are changing more rapidly. In order to capture that and get the results to be more accurate, I need more computational points, more cross-sections at tighter spacing, or more cells at smaller cell size. Some additional things to think about for 2D, though, are that I might need to have refinement and alignment of cells for the channel itself. So I'm picking up the high ground of the main channel bank stations with faces, as we've been talking about all week. And I might also want to change the cell size in the channel so I can get more detail on the velocities. That's an option. And I might even want to add some break lines down the center to align those cells so I get a channel model with aligned cells, so I'm not getting any numerical diffusion of the solution of those equations for the channel itself. Additionally, around roads, levees, and other high ground barriers to flow are going to require break lines in a 2D model, okay? And then at structures, we're going to also need to capture the high ground structures in a 2D model. This is just an example of a model that I put together where the overbank is just a nominal cell size, but the channel, I used a refinement region, and I lowered the cell size, and I also put a break line down the center And so I've got nicely aligned cells with the flow. I've got faces at what I think are the high ground of the main channel banks. So the water's going to stay in the channel until it gets above those elevations of those red lines, okay, and those faces, and then it will spill out. So that's a much more accurate channel model than if I didn't do that. Okay, let's talk a little about friction loss differences. In 1D modeling, both steady and unsteady flow, the program computes a friction slope from Manning's equation at each cross section, but it averages those slopes and divides by 2, adds them together and divides by 2 to get an average friction slope. So the friction losses are based on an average friction slope times the length between the cross sections. 2D modeling, it's a different approach. A friction slope is computed at every face, but there's no averaging. It just uses that friction slope at that face directly when computing the friction losses at that face. So it's just a different approach. Contractions and expansions. In 1D models, when we have a contraction expansion, I need to put in ineffective flow areas. I also need to put in empirical coefficients for a contraction expansion, a C sub E and a C sub C coefficient, which are coefficients multiplied by the change in velocity head. But I need to calibrate those. It depends on how sharp the contraction is, how high the flow is, etc. And then I can also model changes in pressure forces in 1D, but they're modeled in a one-dimensional mode. In other words, only looking at the change in pressure in one direction, not two-dimensionally or three-dimensionally. Now in a 2D model, the two-dimensional flow equations already capture changes in velocity due to contractions and expansions with the acceleration terms and the two-dimensional equations. And the pressure forces are calculated in two directions rather than one. Okay, so contractions and expansions are handled much more accurately with the 2D equations, and you have less empirical coefficients, excuse me. Now, however, in 2D modeling, it may be necessary to turn on turbulence modeling. And then if we turn on turbulence modeling, now we do have some coefficients that are semi-empirical that we have to calibrate, even for a 2D model. Storage and ineffective flow areas. We need to define ineffective flow areas in 1D modeling for all the portions of the cross-section where we're going to have recirculation zones or water not conveying flow downstream. Okay, and we might even need to find storage areas for off-channel or off-floodplain ineffective flow areas. But in 2D modeling, we don't need any of that because the equations bear out the eddy zones and the areas that are ineffective directly based on the equations in the terrain. So we don't need to define storage areas or ineffective flow areas. Hydraulic structures in 1D modeling, as we talked about earlier, we're going to use the options for physics-based equations like energy and momentum or semi-empirical equations, Yarnell, pressure flow, weir flow, or rating curves. In 2D modeling, we can use all those same, what I consider one-dimensional hydraulics approaches, okay, where we're using one-dimensional energy and momentum equation to develop curves for a bridge, or Yarnell and pressure flow, or weir flow equations, et cetera. Those are one-dimensional equations, but we can still use those for hydraulic structures in 2D. But we have the added option of saying, well, let's just actually model the flow through the bridge opening as just true two-dimensional flow with really small cells, or through the gate opening. Okay, so we have that option. Here's an example of a bridge, and we're going to actually look at this bridge in a lot later detail later in the week. And this bridge is modeled with two-dimensional flow. I've got the piers in the terrain. I'm using really small cells, so I'm picking up the effects of water separating around the piers and causing a wake around the piers, okay, and recirculation zones. There's some high ground right here that's blocking the flow, and I'm getting some eddies going around it, okay, et cetera. So this is, if I really needed detailed velocities inside this bridge opening around the piers, this is how I'd have to do it. Okay, let's talk about calibration. So first of all, when we do 1D model calibration, these are the things we generally look at. Predominantly, we look at roughness parameters, contraction expansion coefficients, ineffective flow areas and their extents and their heights, hydraulic structure coefficients. If we have bend losses and we were using bend loss coefficients, maybe. Even boundary condition information such as the energy slope for normal depth, or if I had a rating curve, is it right? Do I have debris blockages? Maybe I need to look at that. And then levee breach dimensions and timing and et cetera. Those are the things I would look at when calibrating a 1D model. Well, a 2D model, I'm going to look at, so here's an example of the Lower Columbia. This is a 1D model I put together a long time ago for the Lower Columbia River. And this is just showing the computed water surface with some high water marks. Okay, so this is the kind of way you look at things when doing 1D model calibrating. For a 2D model, I'm going to do similar things, but modifying the roughness, though, is actually a little bit more difficult because I got to modify roughness spatially, not just at cross sections, and it's more time consuming. The good news is there's no contraction expansion coefficients and no ineffective flow rates, so I don't have to mess with those kinds of things in 2D modeling. However, to get better answers in a 2D model, I might have to refine the mesh in different areas. Maybe I don't have enough detail and I'm not getting the right kind of water surfaces and velocities because I need smaller cells in certain areas, so I might have to do that. And if velocity is really important and a really important output from the 2D model, I might want to get some historical velocity information to calibrate to, if possible. And that might require me to turn on eddy viscosity coefficients and maybe even make some other types of adjustments in n values and so forth in order to get those velocities more accurate, if velocities are a really important output from the modeling approach. So in general, 2D modeling takes a lot longer to make a run. So unfortunately, when you're doing the calibration for a 2D model, you're not going to get as many runs in, and you're not going to be able to like change parameters and see as much cause and effect. So if you're scoping out the calibration for a 2D model, you should actually scope out a little bit more time, just because the amount of time it's so much longer it takes to make the runs, you don't get as much time to change parameters and see what's happening. So let's talk time and cost issues. Obviously, if I'm just doing a quick and dirty model, I can do that in 1D or 2D, but it's actually much faster to do a 2D model if I need something quick and dirty. If I'm doing detailed modeling, I would say that the amount of time to develop a detailed 1D model versus 2D is about the same, to be honest, because yes, in 1D you're laying out cross sections and ineffective flows and so forth, but to get a good 2D model, you can't just lay out a polygon and put in a cell size. You've got to have, refinement regions. You've got to have break lines. You got to test your mesh resolution, et cetera, et cetera. That's time consuming too. Now, after the model's developed, it's probably a little bit quicker to calibrate a 1D model than it is a 2D model, okay? But then the other thing to think about is computational time and hardware requirements. 1D models run just way faster than 2D models. They can run on pretty much any machine. They only require a single thread, meaning one core, okay? And even your basic laptops today have 4 cores, which is more horsepower than a 1D model even needs. And 2D models, though, generally require a much higher level computational machine. You want more cores for the bigger problems. So if you're going to work on large 2D models, I would say you want like 12 to 32 cores, 64 gigabytes of RAM, and an SSD hard disk. Okay, let's talk some advantages and disadvantages of the 2 modeling approaches. So advantages for 1D modeling is it requires less terrain data. We can get away with just surveyed cross sections. Models are often, but not always, easier to calibrate. Hydraulic structures are easier to enter and evaluate and calibrate, okay? And it requires significantly less computational time. Some disadvantages of 1D modeling, though, are we have to know the flow path of the water for all the events a priori in order to lay out the model correctly, because 1D cross sections must be laid out perpendicular to flow to get accurate answers. The other thing is we only get a single water surface at each cross section per time step, okay? And velocity output is limited to average values for left over bank channel and right over bank. Friction losses are average between cross sections, so if our cross sections are far apart, that might not be so great. And the energy losses due to contractions and expansions require empirical coefficients that we have to calibrate, contraction coefficient, expansion coefficient. And then the flow distribution or velocities in an individual cross section are solely based on the conveyance of that cross section, and there's no accounting for what's happening just upstream or downstream of that cross section as far as affecting the velocity distribution, only what's happening in that cross section. And because of that, then also the mapping of inundated areas, it's assumed to be linear between cross sections, so it might be less accurate if the cross sections are far apart. Some areas where 1D modeling generally produces good results compared to 2D modeling with maybe less effort or time, or if we have steep streams that are highly gravity driven with small overbanks, well, that's really highly one-dimensional flow. 1D models are great at that. Even if we have rivers and floodplains that aren't quite as steep, but the dominant flow direction is down the river and down the floodplain, and it's still highly one-dimensional, we've been using 1D models for stuff like that forever and getting good answers, okay? However, when we get to medium and to really large river systems, it might just be required that we use a 1D model just because creating a 2D model would just be too much computational time. So there might be some limitations of 2D modeling when we get to really large river systems that we just might not be able to create, at least not accurate 2D models or really detailed 2D models. And then depending upon how much simulation time, if we're doing period of record analysis, that might require us to do 1D modeling also. And then river systems that contain a lot of structures, it's often easier to put the structures in, look at the hydraulics of the structures, and calibrate coefficients of the structures in 1D modeling as 2D modeling. That's changing though. We're getting better and better with our structure capability in 2D models and being able to evaluate what's happening at the structure. So that's going to change over time. But then the last thing is if the basic data doesn't support the potential gain of the 2D modeling, in other words, if I only have a 10-meter DEM and I have no channel information, am I really going to get a much better model with the 2D model over 1D? Well, probably neither one's going to be very good if I don't have the train data to support it. Here's just an example of a model that's highly one-dimensional. This is the Monongahela and Allegheny River systems in the Pittsburgh district. The channel is, floodplain is very small. It's confined by the terrain. So flow is highly one-dimensional. There's not a lot of spreading out of the flow once it gets out of the channel. And the system's really large. So this 1D modeling works great in this system, and you can get really accurate answers, no problem. Okay, 2D modeling advantages. The flow path of the water for all events does not have to be known a priori. The 2D model will figure it out for you. The direction of flow can even change during time. Velocity, momentum, and direction of flow are more accurately accounted for in a 2D model. Energy and force losses due to contraction expansions are directly accounted in the equations, and you don't need the empirical coefficients so much. But if you turn on turbulence modeling, then there are some coefficients there that you might have to calibrate. Generally, the mapping of inundated areas and velocities and flood hazards is more accurate in a 2D model because you just have more information computed in more detail. And you can do that. You have that option for detailed modeling of structures where we just do full two-dimensional flow through the structure. Disadvantages of 2D models: requires a much more accurate terrain model, including the terrain of the channel underneath the water. Okay. And defining and modifying roughness values is more time-consuming, especially for a calibration period. If you have turbulence modeling turned on, and because it's required in some areas, then you got some empirical coefficients to calibrate there. And it requires significantly more computational time. It just does. So you're going to need a bigger computer, faster computer. You might need to allow for runs just taking longer. One problem I see people doing is they start making the cell sizes larger than they should be, so they don't have as many cells, so the model runs faster. But then you're basically getting a less accurate answer because the cell sizes are too large. And so that's probably not a good thing to do. And the results may not be better if, like I said earlier, if the data doesn't support it. Areas where 2D modeling will give better answers than 1D modeling: behind a levee, if we have a levee breach and the water is going to go in lots of different directions inside the levee, and we don't really know where it's going to go, that's really a 2D thing. If the flow path of the water is not known a priori, if we've got really wide and flat floodplains, the water's going to go out in those floodplains laterally. It's not going to be one-dimensional flow. Bays and estuaries, we want to know and understand the velocities and the intricacies of the velocities. Highly braided streams, alluvial fans, abrupt bends where maybe we have super elevation around the bend, and at hydraulic structures where we want really detailed velocity inside the hydraulic structures. So let's look at some examples. You saw this example the first day. This is that St. Paul. And here's a levee breach, and this water is going to go in all kinds of different directions inside this thing with multiple flow paths and arriving at different locations at different times. There's no way we could get that as accurate with one-dimensional storage areas interlinked. We could get something rough, and we used to do it that way, but now that we have this 2D capability, there's no reason to do that. Here's that dam break that I showed the first day also. Here, this coming out into this flat valley of the Sacramento Valley, there's no way you can predict with a 1D model where the water's going to go. Just not possible, nor the timing of how it's going to get there. So this is absolutely, like, for this kind of region, 2D model is just required. There's no way we could get an accurate answer with 1D. Again, we used to do it with 1D, and we used to get very artful about how we laid out the cross sections, but the answers were pretty rough. Here's something cool. Here's the Lower Columbia River system, and I'm going to plot velocity and velocity tracers. So the first plot is all the water's going downstream, and upstream is on the right, downstream tide's on the left, and all the water's going downstream because the tide's low. Now I'm going to go to another one. Now the tide's coming up, and notice the velocity slow down here, and we start to get some mixing that occurring here, but the velocities upstream are still coming down. Now we're going to go another time step. Now all of a sudden, because the tide has risen enough, water's actually coming in, but there's still water coming from the right down the channel. And then about in here, there's all this mixing. The velocity is really low, but the water's going in all kinds of different directions. And if we really wanted to understand velocities and directions, that's important to our study. There's no way we could at the same exact time get this kind of mixing and changing of velocities in the middle here when we got tide pushing water in and river pushing water down. Just can't do it in a 1D sense. Now here the tide's even higher. So now most of the water is going upstream, except for over here, there's a little bit water coming downstream. So now the mixing point's here. And now the tide goes higher. Now all the water is going upstream. Okay. And we go a step further. The tide's starting to go back down. So the velocities are getting lower. Step further. Now the water is actually going downstream at the lower end, but it's still going upstream up here. And it's mixing with zero kind of velocities in here. Lower tide, now the water's back to going all downstream. Here's another example of a design of a railroad station platform with piers. And this is done in the 2D model. Okay, and we're going to look at first water surface, but then we're going to look at velocities too. So I have the water going out into the overbank areas and hitting the piers, and the existing condition is no piers and no railroad station. Just and so this product study was done to compare before and after of designing a railroad station platform and all those piers. Okay. Okay, at some point, I think I have the wrong animation because it's supposed to zoom in and show velocities. So I think I put the wrong animation in this lecture. Sorry about that. So I think I'm going to skip it. Well, in any event, what you should have seen is we should have zoomed in and seen the colors of the velocity, which we can see here in this picture. You can see how water separates and goes around these piers and eddies behind the piers. You can't get any of that in a 1D model. So knowing and understanding not just the depth of water, but the velocities at the corners of these piers in detail would allow us to decide how can we protect these piers from being eroded or undermined. And so a 2D model at a minimum would be needed for that kind of thing, and maybe a 3D model. Here's an urban area model. Okay, I'm just going to show flow moving. So if I'm in a highly urban area and I want to see how water is going to move through that urban area for higher flows and where it's going to go based on the terrain and the streets and the buildings, etc., that's something a 2D model can really do. As you can see here, we can see where water's going to go, okay, out in the urban area for these higher events. And we're almost done here. Okay, so I think you get the idea.